Good evening, everybody. Okay, can you guys hear me?
Yes.
Perfect, thank you. All righty, so I thought we'd take just a few minutes here, let everybody come in, and we have a full lecture for tonight, but before we start the lecture for tonight, does anybody have any questions that they would like to ask about homework or life or anything else in particular? Anybody have any questions about the homework they'd like to ask?
Professor, I have a question, but it's not regarding the homework. It's regarding the schedule of the final. Is it on syllabus? It says it's on 4th, July 4th. Is it still the same?
July 4th? I think it's August.
I'm sorry, August 4th. Sorry.
Yeah, no, it should be. That's what I got from the Cal Poly. You know, you got to follow their schedule so that you don't have overlapping finals.
You mean, it's August? Oh, I'm sorry, yeah, July, August 4th, right? Okay.
Now you guys got me worried. Okay.
No,
yeah.
no. I was looking at the schedule of the midterm, but then yeah.
Professor,
Okay.
I had a question about the homework. Since we talked about in the office hours, I just want to confirm if you got C close to 36 for number 3. So after that, it's just everything's gonna be right.
I didn't get close to 33.
No, 36. 36.
Yeah, I didn't get close to 36. I got exactly 36.
Okay, yeah, my bad. I mean, what I meant by close to 36, if you didn't want to tell the answer, you know? But yeah, I got 36. Okay, I just wanted to confirm. Thank you.
Yeah, no, I got 36.
Okay,
it's just from similar triangles. So it's basically 003 over 002 times 24 is 36. So yes. Make sure
Perfect.
everybody's on the
Thank
right
you.
page. Okay, the final. We will talk a lot more about that next week. But yes, I have it scheduled on August 4th from 5 to 7:05 p.m. And let's see, August 4th is not that far away, is it? August 4th is 2 Tuesdays. Wait a minute. Holy moly, that's 2 weeks from today is August 4th. Okay, so make sure everybody's on the same page. The final exam is 2 weeks from today on August 4th from 5 to 7:05 p.m. Okay, is that what everybody else was thinking? You guys still there, or did I lose you?
That's good.
Okay, all right. Any other questions? And we have a little bit of time, so if you have any questions about the homework or whatnot, go ahead. Okay, I don't
Professor,
hear it. Yes.
I did have a question. For number 3 on the homework.
Yes, sir.
In this case, since you gave us the strain diagram, we're only gonna be like examining one point, right? There's like 5 points for like analyzing a beam or a column.
Yes, you are correct.
Okay.
Yes, I did not intend for you to do 5 different points and then draw the whole interaction diagram for this particular problem, like I did in all of the examples that I did for you. My intention was that you're just going to analyze one point. So clearly you're not going to draw a diagram just from one point, but you're going to analyze one point like I did those 5 different points. And I intentionally made this one point different than those 5 points that I gave you in all the lectures to make you think a little bit outside the box. When we drew those diagrams, remember the 5 points were just 5 points on a diagram that could be hundreds or thousands of points. When a computer software goes through this, it does thousands of points. So I just gave you another point to look at, but it's not certainly not enough to draw an interaction diagram from.
Okay, thank you.
Okay, sure, no problem. Any other questions? Okay, then we shall start for tonight. Tonight we have lecture 14. And tonight's topic is going to be about the development and anchorage of reinforcement. So what this is going to be about is, even though so far we have considered that when rebar is encased in concrete, that the concrete grabs the little nubbies of the rebar and it bonds to it, and we just never worried about how much actual rebar does it take to develop the bond so that that rebar wouldn't just slide or pull out of the concrete. But we do have to consider that. So that's tonight's topic, is how much development length does it take to actually develop a piece of rebar so that it can go all the way up to its yielding stress and still be anchored on either side of the critical section. So that's what we're going to cover tonight. Starting with older codes required the calculation of the actual bond stresses. So if I have a chunk of concrete, and this is implying a very large chunk of concrete, and I have a rebar that's buried in that concrete for a distance L sub d, and say the rebar is actually sticking out of the concrete, so you could grab it with a ram of some sort and pull it. You could do like a pull test on it. Then the question becomes, how much does this need to be buried into the concrete? How big does L sub d need to be so that when you pull on this, you can develop the full yield of the rebar without actually yanking it right out of the concrete? And the older codes, we would check this by calculating what the actual bond stress was up between the interface between the steel and the concrete. And we don't do that anymore. Bond stress was provided by, so the bond stress is provided by, actually, there really is a bond stress. We're just not going to try to calculate that anymore. It's just not reliable. But there is a actual bond stress. So what keeps this rebar from just pulling out of the concrete, so to speak? And the bond stress is provided by these actions. The first action is chemical adhesion. So there's actually a chemical reaction between the concrete, the cement really in the concrete, and the face of the steel that is sticky, and they bond to each other. If you'd ever pour concrete up against steel, you know that it takes a little bit of banging on it to knock the concrete off of the steel. If there's any kind of oil or form release on it, that makes it a whole lot easier, but concrete will stick to steel. If you have ever witnessed somebody leaving concrete in a concrete mixing truck and they didn't clean it out after they were done, they just left it there, you actually have to get a guy inside of the mixing container with a jackhammer to knock all that concrete off. It really does stick. You also get friction between the steel and the concrete. So as the steel is trying to pull out, there's a friction there between the concrete and the steel. And lastly, you get bearing on the deformations. All rebar nowadays has little ribs on it. Those little ribs are encased in concrete, and you'd actually have to crush the concrete between the ribs in order for the rebar to be able to pull out. So these three actions is what holds or locks that rebar into the concrete. Bond stress is no longer computed because the test used to evaluate allowable bond stress put the surrounding concrete in compression. In a beam, the concrete surrounding the tension steel is not in compression. So in other words, they used to hook up this apparatus, put a rebar in a chunk of concrete, put a testing ram on it, and pull on it and see how much development length it took to get this up to its yield strength. But the problem was that they would kind of lock the whole system together, and this concrete was confined so that it couldn't split or crack in the middle of it. So it wasn't really a fair, true test, because in the real beam, the concrete can do whatever it wants. It can split and it can crack. So instead of doing this now, the current practice is to focus on the development length, L sub D, instead of bond stress. Providing adequate development length ensures that F sub Y can be developed in the rebar without pull-out or splitting of the concrete. So that's what the code is geared towards today, is you plug in some parameters and it spits out what L sub D needs to be. And then it's our job to make sure that wherever this critical section is, that the rebar extends at least L sub D beyond that critical section. So here's a diagram of a more realistic piece of rebar with the deformations on it. And each one of these deformations creates a compression strut, a little micro compression strut into the concrete. So as you pull on the rebar, it's actually tending to split the concrete with a crack right down the length of the rebar. And of course, once the concrete cracks and actually separates a little bit, it allows the rebar to pull out. Anchorage failure is generally the result of concrete splitting. And there's that crack I was talking about. Any questions so far? Okay, so we have types of bond failures. You can have a, so what this is illustrating is around each one of these rebars is a cylinder of concrete. I mean, it's all concrete, but you can picture it like there's a cylinder of concrete surrounding this rebar, and that cylinder of concrete is in tension across the face of it because the rebar is trying to pry that concrete apart, so to speak. So in a beam, if you have all these rebars trying to develop at the same time, it could actually split the beam right down through the center here. And once it splits that beam, you lose development on these rebars. So we have this factor, C sub B, and C sub B is defined as 1/2 of the spacing to the nearest bar less than the distance to the side or bottom face. So if you're trying to develop this bar, I'm sorry, let's do this bar right here. If I'm trying to develop this bar, then C sub B is the distance to the nearest face from the center of the bar, or 1/2 the space to the next bar. Shear stress is on the area between the rebar and the concrete that is around it. Stops the concrete. It stops the rebar from slipping out of the concrete. That's correct. So C sub B is the lesser of the distance from the center of a bar or wire to the nearest concrete surface. So that could be this distance or this distance. Let me get my little spotlight wand here. There, you can see that. Or 1/2 the center-to-center spacing of the bars or wires being developed. So it's either from the center of the bar to this face, or this face, or halfway to its nearest buddy rebar. That's the definition of C sub B. The more rebars you're trying to develop in one plane, and the less distance you have from the center of the bar to the nearest face, then the more development length you're going to need. So more bars in the same face hurts you, and less coverage hurts you when it comes to developing rebar. Okay, so here we got bars on the corner. C sub B is measured from the center of the bar to the outside face or to the bottom face, whichever is the least. CB distance to the side face less than the distance to the bottom, or 1/2 the spacing to the nearest bar. So this is really showing that if you have a concrete beam and you're developing these rebars, that one of the failure modes could be that this rebar develops these cracks going to the side or to the bottom or both. And once this cracks, it can widen that crack and kind of separate a little bit. And then you lose the chemical adhesion, you lose the friction. And at some point, you'll actually lose the bearing on the ribs of the rebar. And so you could prematurely fail a beam at a lower strength than you thought you would because you didn't consider this bond. Actually, if you guys want, I will divulge a insider secret here. You can tell me if this helps or not, but okay, look like that. When I was undergrad, I was doing my senior project at, I was actually an undergrad over there at Cal Poly San Luis Obispo, so the sister campus. And I had decided for my senior project that I'm gonna do 3 test beams. Each beam was 10 inches high, 5 inches wide, 5 feet long. And I did 3 of them. And I built the forms myself, and I bent up little number 3 ties, and I put the main flexural reinforcement in there, mixed up my concrete, did the whole 9 yards. It was really interesting. And then after I cast all 3 of them, we put them into a testing apparatus that put a support here, and put a point load coming right down the middle here. And then we can compare the 3 different kinds of beams that I did. One beam had 2 number 5 steel reinforcement, just 2 regular number 5s. And that was my control beam. My second beam had the equivalent of 2 number 5s, but they were fiberglass reinforced plastic instead of steel right in here. And this was that stuff, this was a number of years ago, but that was the stuff that was advertised as 120 KSI material. So I'm thinking the glass fiber reinforced plastic beam should carry twice as much load because the rebar is twice as strong, right? And then the third one was reinforced with, I think I took 8 5-foot-long pieces of bamboo that I got from Pier 1 Imports, and I cut them in half and reinforced the beam with the bamboo. That was kind of neat. So, won't make this terribly long, but when I tested the beam with the number 5s, as I was testing them, I started getting some cracks that looked like this. And I was starting to get a little nervous. I was like, oh, look at that. Well, they're shear cracks. But I had number 3 ties in there, so I wasn't too terribly worried about shear cracks. That was part of my design. But then, as I'm testing, and we're getting closer and closer to what the ultimate load should have been, the load that crushes the concrete here and yields the rebar here, that load, we're getting closer and closer until I saw these cracks that went right like this, here and here. And no sooner did I see those cracks, and then the whole thing just collapsed. It just like instantly crushed up here, and these big wide cracks appeared here and here, and my beam failed. I mean, literally, it was just 2 pieces of beam sitting on the bench. And it didn't get the final strength. I did not achieve the ultimate strength that this beam was supposed to achieve. Anybody want to take a guess why?
Was your placement of steel incorrect?
Not exactly, but I did. Now, in my own defense, I was a newbie. I mean, I had one concrete design course, just like you guys pretty much have now, and I had one concrete design lab, and I thought I did everything right. And of course, there is a point to the story, hopefully. From the
Professor?
point, yes.
Oh, my bad. I was gonna answer the question. I was saying, did it not bond with the concrete, right?
It did not bond with the concrete, right? That's exactly right. So the point of maximum moment is right there at the midspan, but it still had, say, right here, a very large moment. So I was getting a flexural crack, kind of like that. And it was still a very large moment. And the problem was, which is why I brought up the story, of course, is that the distance from the end of the rebar to this point of very large moment, not the maximum moment, but a very large moment, this was insufficient. The whole beam was only 5 feet long. So that means from the midspan to here is 2.5 feet. That means this distance here was less than 2 feet, maybe 18 inches, 20 inches, something like that. And when the stress in the rebar overcame the development ability of the concrete behind the rebar, it split right here and over here, and we had a bond failure. So the rebar never yielded. It got close. I back calculated to see what it was. I think I got something like 50 something KSI. So it got close, but it never developed the yield. So it failed in bond. And that's kind of a scary thing. I was like scratching my head going, what happened to my beam? But when it fails in bond, it failed very dramatically. It failed suddenly. So that's really a failure mode you do not want to incur. And now, many years later, I hopefully understood what happened. And if I was to do this beam again, what I would do is put little tails on it like this. Because this distance was so small, this was insufficient to develop that bar to the point where I could develop the yield over here. So if I had put little hooks on it like this, then these hooks would grab the concrete better and I would have not had a bond failure. So that was just a little story down nostalgic avenue about, yeah, this really happens. You really do have to think about this because that would have been a catastrophic failure if this was actually something in service.
Professor, but isn't how the concrete's poured with the rebar, isn't that the construction engineer's job, not the one who's designing it?
No, it's not. But that's a good question. But no, it's not. The design drawings, the design documents would show the beam like this. If I didn't show these tails on it, then they have different people working, with the contractor to draw up rebar, shop drawings, and, different phases of construction. But if I don't show these hooks, then the person drawing the rebar would just put a straight piece of rebar in there. So then the contractor or the concrete subcontractor or whoever's building this wouldn't have to put these hooks in there. They would just put in the straight bar because that's what the design document shows. So if I want hooks on this, I have to draw hooks on this or in some way call that out on the structural details. Does that make sense?
Yeah, but the hooks, you said it's only used for if it's a short span, right? If it's short, however, or does it go for longer beams / girders too?
Well, let's get through this lecture. Hopefully I'll
Okay.
answer that. Yeah, hopefully I'll answer that because it's kind of a complicated thing. But suffice it to say that if your critical section, a critical section is just a section where right here on this plane, I need to develop the yield of the rebar. That's all it means. So this is just an arbitrary location somewhere on the beam, but it's saying that right there where that red line is, I want that rebar to be able to develop its yield strength. Well, if that is my critical section, it is my job as the engineer to be sure that on both sides of this critical section, that this rebar is fully developed. And if the rebar is not fully developed, then I need to do something to make it fully developed. Hooks is one option. Headed rebar is another option. Even going with smaller bars is another option because they develop faster than big bars do. But that's on me. That's the structural engineer is responsible to be sure that the rebar is properly detailed at all locations within the scope of what you designed.
Makes sense. Thank you.
Okay. All right. Was nobody curious what happened to the fiberglass reinforced plastic?
Did it fail before the rebars?
Yeah, it did.
Yeah, it was kind of obvious.
What about the bamboo? How did that do?
Bamboo did really good. The bamboo did very well. It did not carry the same load of the steel. The steel took something like 28,000 pounds to fail the beam. Even though it was supposed to have taken over 30,000, it took about 28 or so. I think the bamboo took like 18,000, but that's still pretty remarkable for bamboo. And it was very ductile. It developed cracks and it failed slowly and it deflected. It was really, not a bad option. The fiberglass reinforced plastic, on the other hand, the misconception that I had as a student was that, hey, this stuff doesn't yield until 120, 140 KSI. It must be twice as strong. Well, what they don't tell you is that even though it may eventually be twice as strong, the modulus of elasticity of the material is only a third of what it is with steel. So what that means is as you're trying to develop this very immense tensile capacity, it's straining like crazy. It's like reinforcing concrete with rubber bands. And so the concrete just cracked wide open and ultimately just failed due to the strain failure because the stuff just kept stretching and stretching and stretching. And it never got anywhere near 120 KSI. I think I back calculated that material was somewhere in the 30 to 40 KSI range when the concrete crushed. I was very disappointed. Okay, so back to development. Types of bond failures. Okay, so we're talking about as the rebar is trying to develop, it develops these cracks as it's taking this cylinder of concrete and basically trying to expand it from the inside. And it splits these cylinders. And again, C sub B is the distance to the bottom face or less or half the spacing to the nearest bar. The tendency of concrete to split or crack is reduced by the confinement provided by stirrups or ties. So that's where we're transitioning to the next section. If it wants to crack along these faces here, then if I have a steel tie that wraps around this thing, it's going to tend to keep those cracks from developing. It'll still crack, but it'll keep them from opening up. So having ties around the steel that you're trying to develop helps develop that steel. So here's the plane, the cracking plane from these rebars trying to develop. And this leg, we have two legs of steel crossing that plane. So then we invent this thing called a transverse reinforcement index. per ACI 318, section 25.4.2.3, we have the transverse reinforcing index, which is KTR, equal to 40 times the area of the transverse reinforcement over S times N. So this is not Saturday Night Live. This is not SN. This is S times N, where A sub TR is the total area of transverse steel. For U-bars and ties with 2 legs, then use 2 times the area of the tie. S is the spacing in inches of the transverse steel, and N is the number of bars on the plane of splitting. If the main steel is in more than 1 layer, then N is the number of bars in 1 layer. KTR, K sub TR may be taken as equal to 0 for simplicity if you like. Is certainly conservative. So there's a limit on the effect of spacing in transverse steel. Per ACI 318, section 25.423, the confinement term CB plus K sub TR over DB shall not be taken larger than 2.5. And you'll see where this fits in a second, but you can't, the effect of the ties helping the development is limited. It kind of peters out after a while. Okay, so now the development length per ACI 318, section 25.423. Here's the equation. So L sub D is the length required to develop the yield of the rebar is equal to this whole thingy here, where we have 3 over 40. We have Fy over lambda, remember our lightweight factor, times the square root of F prime C. We have these 3 modifiers, psi sub T, psi sub E, psi sub S. We'll talk about those in a sec. And then here is your confinement term right down here. So you can calculate C sub B, you can calculate KTR over dB, but if this whole term is more than 2.5, then you're limited to just use 2.5. And then the last term here is D sub B. So the actual diameter of the rebar that you're developing directly influences the length required. Where, okay, so lambda is a lightweight factor from lecture 1, varies from 0.75 to 0.85 if you're lightweight, of course, equals 1 if you're normal weight concrete. Psi sub T is a casting position. It is equal to 1.3 if you have more than 12 inches of fresh concrete poured below the horizontal reinforcement. If your bars are vertical, this doesn't apply. But if you have horizontal bars, and when you're pouring the concrete, if there's more than 12 inches below the bar, then you have this 1.3 factor. Otherwise, it's equal to 1 for all other bars. And what is the point of this? If you have, used to call it top bars. So if I have, say like I have a beam, and this is my rebar right there, and you just start dumping concrete into here, well, you're pouring it from the top and it's filling up from the bottom. What the research shows is that you get this little cavity below the bar itself where that concrete is not as well confined or consolidated. And so it kind of undermines its ability a little bit. Okay, does that make sense? Again, if your rebar is vertical, then this doesn't apply. This is only for horizontal bars. Okay, psi sub E is for epoxy coated bars, where you have a factor of 1.5 for epoxy coated or zinc and epoxy dual-coated reinforcement with clear cover less than 3 dB or clear spacing less than 6 dB. It is equal to 1.3 if you have epoxy-coated or zinc and epoxy dual-coated reinforcement for all other conditions, and it's equal to 1 if you just don't have, if you have uncoated or only zinc-coated reinforcement. So, not very common will you run into epoxy-coated rebar. Let me put it this way. Not very common in my line of work means that I've seen it once. We did one job. In over 25 years, I've done one job where we had to provide epoxy-coated rebar. Anybody want to guess where that one job, where that concrete was going?
Was it submerged?
Not quite. Not quite. Good guess, though. Good guess. Not quite submerged. It was actually a bridge that spanned from one side to the other side of a concrete containment vessel located at the Hyperion wastewater treatment plant. So this thing was inside of one of the poop ponds. And it was an environment that I don't think you even want to walk across that bridge, but it was a very caustic and corrosive environment. And so the, let's see, Hyperion is LA County. So the LA County Public Works made us put everything in that thing was epoxy coated. Otherwise, all the other thousands of jobs I've done were all uncoated rebar. Okay, last one was psi sub S, which is a size factor. And it's 1.0 for number 7 or larger bars, and it's 0.8 for number 6 and smaller bars and deformed wires. So what they found is that bigger bars take more length to develop, and that's part of the dB factor that's in the equation, but it's kind of disproportionate. So they just threw in this little extra factor there for bigger bars, and basically you get a little bit of a break for smaller bars. So if you're having a problem with rebar development, one option that you can look at is instead of, say, 3 number 11s, consider using 4 number 9s or 5 or 6 number 8s or something like that. The smaller bar, you still get the same area because you just use more bars, but they will develop faster than the bigger bars. Per ACI section 25414, the value of square root f prime c shall not exceed 100 psi. I've never really gone back and back calculated what that would need to be, but I think it's probably over 10,000. Let's see, 10,000. Oh, okay, it is 10,000. So if you have concrete strengths over 10,000, then you cannot use more than 100 psi for this term. They put a cap on it. Per ACI 318, section 25421. So really, you can go to ACI chapter 25, and all of this stuff that we're doing is in section 4. The minimum length for L sub D is 12 inches. So regardless of what the calcs say, you can't provide less than 12 inches. That's your minimum. Okay, so example 1. If we're given 5,000 psi concrete, the rebar is 60 ksi, I have this cantilever situation where maybe this is a wall and I'm just cantilevering this beam off of the wall. The question becomes, if I have 3 number 9s, how far back do I need to extend those number 9s into the concrete wall to be safe that when I load this, it will fully develop its yield before it yanks those bars right out of the wall? How far does that need to be? Over here on the side, I've got some dimensional information. These bars are spaced at 7.5 inches apart, and they're 2.5 inches from the face, typical. So that would be to the side or vertically. concrete is normal weight, bars are uncoated. More than 12 inches of concrete will be poured below the bars. See, the bars are at the top here, so when they're pouring this, it's going to drop to the bottom of this more than 12 inches. So we do have a top bar situation. No transverse steel is provided in this case. So what is required? Find the required development length L sub D. Okay, do I have any questions about the setup here or what I'm doing? Any questions at all? Okay, so working through our solution, here's my equation. L sub D is equal to all of this, where, and so I can start plugging in these values. Lambda is 1 for normal weight concrete. Psi sub T is 1.3 for top bars. Psi sub E is 1.0 for uncoated bars. Psi sub S is 1.0 for number 9 bars. C sub E is the smaller of half the spacing of the rebar, so 7.5 over 2 equals 3 3/4, or center of bar to the nearest face is 2.5. 2.5 is going to control. KTR, K sub TR, we're going to assume is equal to 0 because I have no transverse steel in this case. DB is 1.128 inches for a number 9 bar. And by the way, as long as I've got most of you on the line here, looks like maybe 2/3 of you are on the phone right now. I want to be sure that nobody is still trying to calculate the area of rebar by using pi over 4 times the diameter squared. That may get you close. It may not get you close, but it's never the right answer. Okay, this is just kind of a pet peeve, but I was grading homework set number 7. So we've done 7 homeworks now, and some folks are still using pi over 4 d squared. Please do not do that. If you're not sure what the area of the rebar is, it's easy enough to look in your textbook and just look it up. Okay? Can I get off my soapbox? Is that clear on everybody?
Yes.
Yep.
Yes.
Okay, very good. I know none of you did that, but somebody did. So just want to make sure that is clear. Your diameter must come from the table. Your area of steel must come from the table. And just a point at note, that's what kind of reminded me of that pet peeve. This is not 9/8. It's close, but it is not 9/8. And the bigger the bar gets, the more it differs from just using its number in eighths as a diameter. Okay, enough of that. From the tables, the diameter of a number 9 bar is 1.128 inches. And so I plug in all my values into this rather cumbersome equation. You can see the 1.128 goes here and here. And my total is 42.1 inches. Oops, let me go back here. And you know what? I didn't check, but you should verify that this term right here is not greater than 2.5. Clearly 2.5 over 1.128 is less than 2.5, so I'm okay. But this is a point of note. Please be sure that you check that your confinement term is not greater than 2.5. So 42.1 inches. Before we get to example 2, I just want to make sure that we are clear that when I'm detailing this rebar, I must be clear on my drawings in one way or another, doesn't matter how you do it, but you have to have at least 42 inches from the end of this bar to the critical face of this wall, and that has to be detailed on your drawings. Any questions about that? Okay. So this is my drawing. It's not quite what you would see on a design drawing. A design drawing would have a better geometry, not just kind of a symbolism showing a bigger wall here. But what I'm saying is on your drawings, it would look a lot like this. You'd say, you know, this is the dimension of the cantilever. You'd have some dimensions on the section. You'd call out your 3 number 9 bars. But you have to be very careful in a situation like this that you define the minimum length from the end of the bar to the face of that wall, so that a detailer or rebar provider doesn't just assume, all right, I'll just make this 3 feet. That should be good. 3 feet is not good. It's not good enough. You need 42 inches. So you, as the engineer, have to define this and put a dimension on it and say 42 inches minimum. The green line is the wall, yes, or the green line is the concrete. Okay, does that make sense to everybody? Okay. So for the number 9 bars, we're looking for 42.1 inches minimum. Example number 2. Given concrete is 3,000 psi, rebar 60 ksi, and here we have a situation where we have a beam. So this is a break line. So the beam keeps going off to doing something. But the beam cantilevers over the support by some unknown amount. And what we want to know is, given these parameters, how far does this rebar need to extend beyond the support so that it is fully developed at the support? So this is where I want to fully develop my rebar. How much more does it need in order to be fully developed at this point? That's what we're looking for. The rebars are 3 number 7s this time. I have 2.5 inches typical from the bar to the face. And with 20 inches, you could calculate what that spacing is in between there as well. And I do have transverse reinforcement. I have number 4s at 6 inches on center. And you can see from the section that I have 2 legs of the number 4 tie. Concrete is normal weight. The bars are uncoated. And as you can see from the illustration, there will be less than 12 inches of concrete poured below the bars. Transverse steel is provided. Required. What is the development length L sub D required to guarantee yielding at this point? Solution, here's my equation, where lambda again is 1.0 for normal weight concrete. Psi sub t is 1.0 for top bars. Actually, well, they're not top bars, but it's 1.0 for bar position. Psi e is 1.0 for uncoated bars, and psi sub s is 1.0 for number 7 bars or larger. C sub e is the smaller of half the spacing of the rebar, so that's 7.5 over 2 is 3 3/4 again, or the center of bar to the nearest face is 2.5 inches. C sub b then is the lesser, so 2.5 inches controls. So my reinforcing index, my confinement index, K sub tr is 40 ATR over SN. ATR is 2 legs of number 4 bar, 0.40. S is 6 inches on center. And N, I have 3 bars. Let's go back and look at that. I am trying to develop 3 number 7s in one plane. So if developing these bars tries to split this plane, I've got 3 of them within that plane. So N is 3. N is equal to 3. So K sub TR is 40 times 0.4 over 6 times 3 equals 0.89 inches. So therefore, CB plus KTR over DB is 2.5 plus 0.89 over 0.875 equal to 3.87. 3.87 is greater than 2.5, so you have to cap it at 2.5. dB is 0.875 for a number 7 bar. And so I plug in all my values, my yield, my concrete, my lambda, psi t, psi e, psi s, my 2.5 times 0.875 dB, and I get 28.8 inches. That's the minimum distance to develop those number 7s. Okay? Do I have any questions about developing straight bar? Okay. So as I mentioned earlier, if you don't have enough room, an option then is to hook your rebar so that it grabs the concrete quicker and you don't need as much development length. So the development of hooked reinforcement to reduce the required distance to develop reinforcing hooks may be used. And here's an example. So if this is my critical plane, then we define L sub DH. L sub D is for straight bar. LDH is for hooked bar, okay? And the distance is from the critical section to the back of the hook. And then the code defines the minimum hook length as 12 times the diameter of the bar. And then we have this minimum radius here. When you bend the rebar, this radius is a function of the bar diameter. So the bigger the bar diameter, the bigger this radius has to be. So you basically don't break the bar, fracture the bar when you're bending it. Here's a card. You can download these. We used to get them in the mail from CRSI. Don't ask me what that stands for at the moment, but CRSI are the rebar guys, and they put out these plastic cards that kind of little quick, handy information. And it tells you what the minimum hook lengths need to be, tells you what this dimension A or G, that's the hook length. The extension is from the center of the bend to the end is 12 dB, that's this category. The finished bend diameter D here, that's the pin that you actually bend the rebar around the steel pin. These are defined here. Look at that. For a number 18 bar, this steel pin has to be 2 feet in diameter. That is ginormous. I'm used to number 5s and 6s and 7s with a 4.5, 5.25 inch pin. And there's your nominal diameters. So these are handy. Like I said, for years and years and years and years and years, I had little plastic cards that I had thumbtacked to my bulletin board. And now that I am COVID sequestered, I don't have my bulletin board, so I downloaded these from the web under CRSI. Okay, so ACI 318, section 25431 specifies LDH as the greater of A or B or C. A is an equation that looks a lot like the straight bar equation, just a little simpler. B is 8 times the bar diameter, much simpler. And C is just a flat out 6 inches. This can never be less than 6 inches for any size bar. Lambda, lightweight factor from lecture 1, 0.75 to 0.85 for lightweight, goes here. Psi E is your epoxy, where this is actually different though. Be careful about this. Psi E is not the same values as it was for straight bar. So now for hooked bars, it's 1.2 for epoxy coated or zinc and epoxy dual coated reinforcement, and 1.0 for uncoated or zinc coated reinforcement. The other one had 1.5 and different, is a little different. So Psi E is not the same straight bar to hook bar. Psi C is cover, and it's equal to 0.7 for number 11 and smaller hooks with a side cover, normal to the plane of the hook, greater than 2.5 inches, and for a 90-degree hook with cover on the bar extension beyond the hook, greater than 2 inches. Okay, so in this illustration, that means from the back here to the face is at least 2 inches, and from the side plane to a face of concrete going in and out of the page, at least 2.5 inches. Almost always the case. And then you get the 0.7. If you don't have this, then it's 1.0. And psi R is for confining reinforcement. It is 0.8 for the 90-degree hooks of number 11 and smaller bars if they are enclosed along LDH within ties or stirrups perpendicular to LDH at S less than 3 dB, or enclosed along the bar extension beyond the hook, including the bend within ties or stirrups perpendicular to L extension at S less than or equal to 3 dB. And it's equal to 0.8 for 180-degree hooks of number 11 and smaller bars enclosed along LDH within ties or stirrups perpendicular to LDH at S less than 3 dB, and 1.0 for other. Okay, that was a mouthful. Here's the illustration. Here's my bar that I'm developing right here, and here is my hook length here. So if I have ties in this region spaced less than or equal to 3 dB, dB being the diameter of the bar being developed, or I put them in this direction at a spacing less than 3 dB of the bar being developed, then I get this little bonus here, 0.8. If I don't have this situation, either of these situations, then psi sub R is 1.0. Any questions on this?
Professor, where does the 2 dB play?
The
'Cause
2
it
dB,
says-
yeah,
okay.
yeah, good question. That just means that the first one has to be very close to the end of the bar,
Oh, okay.
or
Okay.
very close to the top of the bar. So you can't have like this big old hook and then you just put a bunch of ties way down here. That's ineffective. It has to be close to the top.
Okay, makes sense. Thank you.
Okay. ACI 318, section 25433, if both side cover and in cover are less than 2.5 inches, then A through C will apply. Where the hook shall be enclosed along LDH within ties or stirrups perpendicular to LDH at S less than 3 dB. The first tie or stirrup shall enclose the bent portion of within 2 dB. And psi R shall be taken as 1 in calculating LDH in accordance with that equation that we had. In other words, basically what we're saying is that if the end cover and the side cover are both less than 2.5 inches, then you have to do this. You have to tie these things to keep them from blowing out the side. Okay, ACI 318 table 2531 gives the straight extension of the hook as a minimum of 12 dB. ACI 318 section 25410.1 and 25410.2 allow a reduction of development length of straight, hooked, or headed reinforcement, which we haven't talked about yet, but not less than the applicable minimums for excess reinforcement. If you have more rebar than you actually need, then you can take a little reduction in the development length to account that you have more steel than you actually need. So LD, LDH, or LDT, which we haven't talked about yet, can be reduced by a factor of AS required over AS provided unless you're at non-continuous supports at locations where the anchorage or development for FY is required, where bars are required to be continuous. And for headed or mechanically anchored deformed reinforcement, and in seismic force resisting systems and structures assigned to seismic design categories D, E, or F. In other words, if you designed this as a moment frame in a seismic resisting frame, then you can't take this reduction. Okay, let's do example 3, then we'll take a quick break. Example 3, concrete is 4,000 PSI. Your yield is 60 KSI. Here is our old friend, the cantilevered beam off of a wall trick. But now I want to develop this with a hook instead of straight bar. I have my 3 number 9s. Here's my spacing, the same as before. I want to calculate what is the minimum length from the critical section to the end of the bar. And again, I want to make sure everybody is clear that if I put a big heavy weight out here, the thing is going to try to fail right along that face. So that's my critical section. Concrete is normal weight. The bars are uncoated. The back cover and the side cover are greater than 2 inches. Transverse reinforcement does not meet the requirements for confining reinforcement. So I may have transverse reinforcement in here, but it doesn't meet that 3 dB requirement. What is the required development length L sub DH? Solution, it's either A, B, or C. A is the equation where lambda is 1. Psi sub E is 1 for non-coated bars. Psi sub C is 0.7 for coverage and 1.0 for unconfined bars. D is 1.128 for a number 9 bar. I plug those into the equation and I get 14.98 inches, 15 inches. Or 8 times dB is 9 inches or 6 inches. So clearly from A, B, or C, A controls at 15 inches. Okay, any questions on hooked reinforcement? Okay, so let's take a 10-minute break, and or maybe just a little less. Let's reconvene at 6:10. Okay, I'm back. Who's awake?
Still here.
Still here.
Yay. Okay. Let's knock this thing out. Okay, so far, we have talked about developing straight bars. We've talked about developing hooked bars. Now we're going to talk about headed reinforcement. So to reduce the required distance to develop reinforcement, heads may be used. And this is an illustration of, so here's your critical section. You're pulling the bar out this way. This is a rebar that may actually have like a head, like a stud head formed into it by heating up the bar and using a process that squishes it to a head. Or it could be, there's any number of products out there where the head has female threads in it, and then the rebar is threaded on the end, and you spin the head onto the end of the rebar and develop it that way. And or there's any number of products out there where you just take a steel, round piece of steel or a square piece of steel stock, and you weld the rebar to the head. We don't do that. The manufacturer does that. And so it's a manufactured product, but you can use it in places where hooks don't fit very well and you just don't have enough room to develop a straight bar, then you can go with these headed rebars. In my line of work, in my field, we actually use these quite a bit because I'm in the precast world. And in the precast world, you build pieces of concrete to a defined shape. There's an end to the beam, there's a side to the T or whatever. And so a lot of times things don't fit, whereas in the cast in place world, everything's poured together. So there's usually a lot more room to run rebar out of the beam into the column and so on and so forth. So this is a detail used a lot more in the precast industry, I would think, than in the cast in place. Okay, so ACI 318 section 25441 specifies that heads can be used when all of the following conditions are met. The bar shall conform to 20.213, which is ASTM specifications for A615, A706, or A995 rebar. The bar yield shall not exceed 60 KSI. The bar size shall not exceed number 11 bars. And this is just due to limited testing data that they have. The net bearing area of the head shall be at least 4 times the area of the bar. So the net area of the head is the underside of the head there minus the bar itself. So this actual area, square inches of steel bearing up against the concrete that keeps the bar from pulling out. Concrete shall be normal weight. The clear cover from the bar shall be at least 2 diameters. That could be to the side or to the any side really. And clear spacing between bars shall be at least 4 dB from this bar to the next bar. ACI 318 section 25442 specifies LDH as the greater of A or B or C, where A is the equation form, LDH, actually that's supposed to be, I did it again, guys, sorry. This is LDT and LDT here. LDT are equal to 8 dB, or LDT is equal to 6 inches. Psi E is your epoxy factor. That's the only factor left in this equation. And it's 1.2 for epoxy coated or zinc and epoxy dual coated reinforcement, and 1.0 for uncoated or zinc coated reinforcement. F prime C in this equation shall not exceed 6,000 PSI concrete. It's kind of interesting. So they put a much more tighter restriction on this term here. So here's an example of what these look like. This is from a company. There's many companies that will do this, but this particular company is called HRC. They're in Fountain Valley, California, and they manufacture this piece of rebar with the head kind of already formed or squished onto it. So what you do is you order these by size. So like number 8 bar is what this is illustrating. And then you tell them how long you want the rebar to be behind the head. And then they'll make those to your order. This is a different type. This is where you have, oh, this, yeah. Okay, so this threads onto this piece here. And so this is a solid steel piece that threads onto the rebar piece. So male and female pieces. Okay, any questions on headed rebar? Okay, so the next topic is development of welded wire fabric in tension. So here we have our critical section, and we have a welded wire. This is going to be a deformed. Welded wire comes in two main styles, either plain or deformed. They're both made out of wire. And what's the difference between wire and rebar? Well, rebar is rolled from raw material. It is melted in a giant cauldron, and then it is, let's see, oh, then they form it into ingots, and then they take the ingots to the other side of the facility. They melt those ingots down into liquid steel, pour the liquid steel into these, actually it's a continuous rolling process, but it pours the steel into, it's like a giant wheel with the shape of a rebar kind of formed into it, and it rolls that sucker out, and then at specified lengths, and then at 20, 40, 60 feet, they basically snip it off, rolls down, and then you have a piece of rolled rebar. Wire is a little different. Wire is a material that is rolled between these dies, which squishes it kind of to the exact size that you need, but it's like a continuous process. And the wire is rolled into these giant spools, which may have, I don't know, half a mile to a mile of rolled up wire on one spool. And then different fabricators will take the spools of wire to their facility, and they'll use them to almost robotically create these meshes. So you have a bunch of wires going east-west, and you have wires going north-south, and it forms like a mesh. And then those meshes is a manufactured product that then gets shipped to whoever's casting the concrete, and they'll use those meshes to reinforce the concrete. So this now is illustrating, this is not a rebar. This is a piece of wire. And as I said, the wire can either come plain, which means it's just a smooth piece of wire. These wires can be anywhere from smaller than a pencil to about as big as a number 5 rebar, pretty much about the size of your thumb. So from the size of a small pencil to the size of your thumb is the sizes that these wires come in. And again, they come as deformed or plain. Plain is just a smooth wire. Deformed, they run it through a machine that it doesn't form ribs on it like a rebar, but it's a dimpling machine. It actually like pinches the wire and forms these dimples, and it kind of helps it develop a little quicker. So, having said all that, if the welded wire is deformed, then this is what you have. You have to have a cross wire, and that cross wire has to be at least 2 inches from your critical face. And then you have to have a tail on it beyond that cross wire that is equal to LD. So ACI 318, section 25462 specifies that LD is found from ACI 318 25422 or 25423, which is the equation we covered at the very beginning of this presentation. multiplied by a wire factor psi sub w found from 25463 or 25464. So in other words, you basically treat this like a piece of rebar, but you have to multiply it by this psi w for wire. ACI 25463 states that if you have at least one cross wire located at least 2 inches from the critical face, then psi sub w shall be the larger of, it's either Fy minus 35,000 over Fy or 5 dB over S, the spacing, where S is the spacing of the wires being developed. ACI section 25464 states that if there are no cross wires, then psi W equals 1, and you basically treat it like a piece of rebar. ACI section 25462 allows for epoxy-coated rebar that psi E equals 1.0. And okay, so now let's move to plain wire. The deformed wire needed 1 cross wire. Plain wire reinforcement needs 2 cross wires, the first one being at least 2 inches from the face. So ACI 318 section 25471 states that 2 cross wires are required, and LD as the greater of this equation here, or LD is the spacing of the cross wires plus 2 inches, whichever is greater. So if the space between the 2 wires is 6 inches, then this needs to be at least 8 inches. Where S is the spacing of the wires being developed. S goes right there. Okay, any questions? I know I went through that kind of quickly. It's kind of a niche market. You know, you may or may not even really see this in a concrete career, but just so you know that it's there, that welded wire mesh is treated separately from just plain good old rebar. Any questions on that? Okay, let's talk about compression steel. So here again, I have a critical section, and I need to know how much rebar does it take into my critical section to develop the full yield of that rebar, but in compression, not tension. What do you think? Should it be less or should it be more if it's in compression?
Probably less, right?
It is less. Yes, it is. Takes less because you have this bearing at the end here. So in order to fail this pushing the rebar into the concrete, you basically have to crush the concrete right on the tip here, kind of like driving a spike into this thing. For deformed reinforcing bars and deformed wire in compression, ACI section 25492 gives LDC as the greater of this equation here or this equation here. Whichever of these two is greater, that's the one you have to provide, or minimum 8 inches. In this equation here, you have your lambda, lightweight factor, and you have psi sub r is your confining reinforcement factor. If you're putting this in compression, you tend to be, again, splitting the whole section. And if it's tied together with confining reinforcement, you get a better value. Confining reinforcement psi sub r is 0.75 for reinforcement enclosed with any of the following: a spiral, a circular continuously wound tie with dB greater than 1/4 inch and a pitch less than 4 inches, or number 4 bar or D20 wire ties in accordance with 2572, spaced at less than 4 inches on center. Or hoops in accordance with 2574, spaced at less than 4 inches on center. And if you don't have that much confinement, then you just use 1.0 for any other case. Okay, that was it for compression steel. Any questions? Where would you expect to see something like that, you think? Where might that come up? Well, yeah,
Cantilever beam? Oh,
possibly, yeah, cantilever beam on the bottom of the beam where you're in compression. Yes, that would be one place. I'm thinking where it comes up probably most commonly, and I'll draw a little diagram here, where it comes up a lot is if you have a concrete footing, and on top of this concrete footing, you have a concrete column. And if you don't have a lot of moment, but you have a lot of axial load on that column, then you could have these rebars going into the foundation. And you better be sure that you have enough development from the bottom of the column to the bottom of the rebar to develop that rebar in compression if the load is, pushing down this whole thing in compression. If you don't have enough room, then what could happen is either the bars could crush the concrete and slip into the foundation, or if it's like how I've drawn here, you could actually punch these bars right through the bottom of the foundation. Neither of those are very good. So that's where that would come in. That's where, as a designer, you got to make sure that you've checked this, that you have enough room in here to develop those bars. Okay. Do I have any other questions before we move on? Okay. Now what we're going to talk about is reinforcement cutoff points. So here I've got a cantilever beam, and I've got two rows of steel. I've got these bars A at the top, and I got these bars B just below them. For a cantilever beam, here's my moment diagram. As you can see, at the support, I have my maximum moment. So I need all the bars I can get at my maximum moment. But the moment drops quite a bit as I get out into this span. So do I really need to carry all of this steel all the way to the end of the beam? Structurally, no, I don't. It's right about here is where I have half the moment. So you would think I could lose half the bars if I only have half the moment. So that's the idea of reinforcement cutoff points, is for economy. You don't always have to take the steel that you need right at the maximum. You don't have to carry it all the way through all the time. The other thing, remember this came up, is when we're looking at one-way slabs. And remember, we were looking at, you need some steel in the top for the negative moment. You need some steel in the bottom for the positive moment. But you don't need to carry that steel all the way through the whole span. There, you can cut it off as you don't need it anymore. So that's the idea of calculating reinforcement cutoff points. ACI 318, section 973, allows bars to be terminated when they are no longer needed for moment resistance. We start by plotting the phi-mn diagram on top of the mu diagram, like so. So this is mu, is what you would calculate from your mechanics of materials class. Phi-mn diagram. So this is the capacity of bars A and B. So all the bars develop a moment capacity down to here. Why is this beveled like this? Why doesn't it go right to the end of the beam? Anybody?
because of that little edge that doesn't have steel.
Pretty close, because right at the end of the beam, you have no steel. That's absolutely true. But just a hair inside of the beam, you have steel right there. But that steel has almost no development length. The straight portion of steel beyond this point is nothing. So with no development length, you have no capacity. And as you move along, you start building up development length, but it takes you this long, this distance here to get to full development length. Okay, so that's what we were just talking about, is L sub d, the development length. It takes this much room to fully develop that rebar to the yield. Once you get this horizontal line represents these bars fully yielded. So this is your total capacity strength here, but this is that L sub d that I was just talking about. Right there, okay? So as you go from 0 development to full development, then the capacity of the beam is developing linearly. And it's okay to analyze it as linear. So if you got half of your required development length, then the code says you get half of your capacity. Does that make sense? So that's why this doesn't, you don't have full capacity all the way right out to the end of your bar. It takes a while to develop those bars like so. And that's why you have this sloped portion. But to the bigger point, look at all this area out here. Right here, you can see I clearly need all those bars because I'm just a little bit greater phi-min than mu, which is what you want. But over here, I've got way too much steel for the actual demand. Anywhere in this region, I've got way too much steel. So it seems like we could reduce the steel as we're moving out. From the overlay of the phi-min and the mu diagram, you can see that phi-min is greater than mu at all points. So as I progress along the length of this, the blue line is always below the red line. And this is a negative moment, so that's why these are negative. If it was positive moment, it would just be the flip side on the top side. Okay, does that make sense to everybody? Is everybody tracking with what I'm trying to do? Is anybody tracking with what I'm trying to do?
Yes, Professor.
All right. As long as I got one person still alive. All right. Okay, more than one person. Great. All right. So as I was saying, as I was showing, this is L sub d. This is the length it takes to develop these bars. At the termination of the bars A and B, we have a linear progression of strength as the bars are developing within the L sub d length. Once you get to L sub d, you have your full capacity based on the yield of the bar. For most of the span, phi-min is much larger than needed. Therefore, some bars can be terminated early. Not all the bars, of course, because then you have no capacity, but you could take some of these bars and just stop them early. Okay, so we can point, the point where the moment is half mu, okay, what I meant to say is we can find the point where the moment is half of mu and terminate bars B where they are no longer needed. This is assuming bars B is half of the total bars. So we can find where the demand is half of the end demand, and we can locate where we can get rid of some of our bars. Okay, so at this point here is where my moment demand is half. Theoretically, we could terminate the bars exactly where they are no longer needed, but ACI 318, section 9733 specifies that the bars must be carried at least a distance of d or 12 dB, whichever is greater, past the point where they are no longer needed. Okay, so even though right along this dashed dotted line, the moment is half, so we could get rid of half the bars. But the code says not so fast. You got to go at least beyond that point of needing half of what you have by the greater of D or 12 times the bar diameter. D is the depth of, from the compression to the tension steel, or 12 times the diameter of these bars here. So we got to have a little buffer in here. It's just a bit of conservativeness. And it also has to do with the way that the shear mechanism works, that it kind of exaggerates the tensile requirement beyond where the flexural response is. Don't need to worry about that too much, but just suffice it to say that where the code says you don't need it, or where mechanics says you don't need it anymore, go beyond that by D or 12 times dB. Okay, so then we're going to carry these bars out a little bit beyond where we need them, and we're going to construct a revised VMN diagram based on cutting half of these bars. And this is what it's going to look like. Okay, so the capacity of just the A bars is right here, because I have at this point my fully developed A and B bars, but I stopped my B bars here. So over here, all I have is my A bars. This is my capacity of just the top row, the A bars. And then we have these slope portions, because it takes a little while to develop the A bars from the end of the A bar. And again, it takes a little while to develop the B bars from the end of the B bars. So this is what my VMN diagram looks like. And again, we construct this in such a way that we can visually look at it and say, okay, I still have more capacity at every given spot than the actual demand, as shown by the red line. Okay, if you don't, then you need to adjust where you're cutting your bars down so that you do. You always have to have your capacity greater than your demand at all locations. Do I have any questions on this? Okay, so why? What's the point of this? Why would I bother doing something like this? Well, the way that I drew it is, of course, the most simplistic way to just kind of illustrate a point. And a cantilever is pretty easy to visualize. It's going to crack at the top, it's going to crush at the bottom. So this is all negative moment. But if we don't have some kind of a mechanism to do this, it's not just beams. This could be walls, it could be shear walls, this could be diaphragms. We build concrete garages where the diaphragm is 300 or 400 feet long. And if I need 60 number 8s at the midspan of the diaphragm, if I have to carry all 60 number 8s to the end of the diaphragm, that's hundreds and hundreds of feet of many, many bars. And it's unnecessary. It's just an unnecessary expense. So I would like to cut those down. I would like to go from 60 number 8s at the maximum moment to 40 number 8s to 20 number 8s. Maybe I only carry 10 number 8s out to the end. And you can save quite a bit of money by just not putting rebar where you really don't need it. Okay, so that's kind of the point of the whole presentation here. Everybody tracking, or did I lose anybody completely?
By the way, can you see when we give you a thumbs up?
A thumbs up. No, I just, can I bring this over here? Can you see that? Can you see the Zoom group chat?
No.
No.
Okay, never mind. But that's all I can see. I can see who's muted, I can see who's talking, and I can see the Zoom group chat where some folks like to just say, yes, I'm awake, I'm here, but no, I haven't seen a thumbs up.
So I don't know about the other students, but I know in my other classes, myself and my other peers give a thumbs up whenever the professor asks if we're following. So you know you're not just there and awkward silence, you know.
Yeah, that'd be great. I feel like I'm talking to myself.
Yeah.
But no, I don't see any thumbs up, unfortunately. Maybe I'm doing something wrong. But I do see when people Zoom group chat or on the chat do the private chat, I see that. The thumbs up is in the pictures. What
Yeah,
pictures?
I could see when my classmates are giving thumbs up. Right now, I have Edgeman Ting giving a thumbs up.
I am not seeing that. Oh, you know what? Probably because I'm sharing my screen and you guys aren't. So you're seeing, I don't know. Anyway, just from time to time, I will ask an open-ended question. If somebody would just say, hi, I'm awake, yeah, I'm getting it, then that's all I need, I guess.
All right, sure.
Okay. So, and we're not too far from the end here, so we're doing pretty good. And we confirmed that phi-min diagram covers the MU diagram at all locations. So again, this is all upside down because this is negative bending. If this was positive, then the red line would be above and the blue line would be above that. See, so if it's negative bending, you're below the axis, positive bending, you're above the axis, but still the whole concept is you build this phi-min diagram and then visually confirm that you're always above or below your required moment. Okay. ACI 318, section 9735 gives further restrictions on the cutoff points for flexural reinforcement, stating that at least one of the following must be satisfied. If you're going to cut off bars, then the VU has to be less than or equal to 2/3 of your phi VN. Again, there's a kind of a complicated behavior between the shear and flexure that if the shear is high, what it does is it pushes the tensile requirement more towards the support. So they just have this requirement that has to be checked. For number 11 bars and smaller, continuing reinforcement provides double the area required for flexure at the cutoff point. Continuing reinforcement provides double the area required for flexure at the cutoff point, and VU is less than 3/4 of phi VN. Or the stirrup or hoop area in excess of that required for shear and torsion is provided along each terminated bar or wire over a distance of 3/4 D from the termination point. Excess stirrup or hoop area shall be at least, and there's some equations. Now that's it. So A, B, or C. So basically, going back to the example that I did, you probably would just want to confirm that your maximum shear, VU, at the point that we terminated those B bars is less than 2/3 of phi VN. ACI 9738 gives further restrictions on bar cutoffs and continuation of rebar at supports and inflection points, which are beyond the scope of this course. Okay, rebar splicing. There are many cases where rebar must be spliced, either because of the staging of construction or maximum available length of the bars. Again, I mentioned a minute ago that one of the common things that we do for concrete garages is we have diaphragms. That's the actual concrete floor, but it's like a beam laying on its side for seismic loading. And these diaphragms can be hundreds of feet long. You can't buy rebar that's hundreds of feet long. As far as I know, the maximum length you can get is about 60 to 80 feet or so. That's it. So that means you're going to have to splice rebar. or go the other direction. Everybody's familiar with the tallest building in the world as of today, the Burj Khalifa. I'm sure you guys have heard of it. Okay, so this is a reinforced concrete building. The whole building, except for maybe the last couple 100 feet, is a steel spire, but the rest of the whole building is concrete. And the main lateral force resisting system of this concrete beam are concrete shear walls. Well, at the elevator core, right in the center of the building, these walls are somewhere around 2,700 feet tall. So you got to imagine there's a lot of splicing going on if you can't get rebar more than 60 or 80 feet tall, and this wall is 2,700 feet tall. There's going to be a lot of splicing. So because of the way that the construction is staged, that meaning like you can only pour, the Burj Khalifa was poured like one floor at a time. And then you got to have rebar sticking out of that floor. You can only have it sticking out so far. And then you tie in the next floor, you got to splice those rebars together. So reinforcing can be lap spliced, mechanically spliced, or spliced with welded connections. Lap splicing will be covered here. Okay, so here's just some nondescript concrete element. And I've got rebar, and for whatever reason, it had to terminate at this point, but I needed to continue. So I have a lap splice between two pieces of rebar. ACI 318.25.521 defines two types of splices, type A or type B. For a splice to qualify as type A, the area provided over the area required must be at least 2 times at the location of the splice, and no more than 50% of the total reinforcement is spliced at one location. So you can see right here, I got 2 times the required rebar because I got 2 bars instead of 1. But if you're splicing multiple locations, you just have to be sure that you always have at least twice the steel required within this lap splice region. And the other is you can't splice more than half of your total steel in any one location. So if you need to splice a whole bunch of bars, you do some of them here, then you move over and do some of them here, then you move over and do some of them here. You have to stagger how you're splicing that rebar. If the splice doesn't qualify as type A, then by default, it is a type B. For type A, LST, which is the lap length, equals the greater of 1 times LD, or 12 inches. For a type B splice, LST equals the greater of 1.3 times LD, or 12 inches. Did I have a question? Okay, so a type A splice is more stringent, but if you have met the requirements of a type A, you get a little bit better. You only have 1 times the development length of the rebar. If not, then you have 130 times, 130% of the length, splice length of that rebar. And ACI 25.522 states for bars of different sizes, LST shall be based on the larger of the 2 bars, 2-bar LD lengths. So in other words, if you're splicing number 11s to number 9s, then you would base this LST on the development length of number 11s. Okay, so that is today's presentation on rebar development. Any questions at all?
Professor, I had a quick question.
Sure.
So whenever you're splicing, don't you get like the diameter of it goes on the top? So wouldn't that go into the clear coat that you have to, the clearance? How do you manage doing the clearance? So your D changes, everything changes in that moment, doesn't it?
Not necessarily, but that's a great question. So you have different conditions. You could have a beam, And if you have to splice rebar in the beam, then maybe the green rebar needs to be spliced with blue rebar. So you could put these side by side so that that's a horrible drawing, but so you see your effective D is not changed. And then your green rebar would stop, and then your blue rebar could start. These could be very close to each other. And then it doesn't take very long where you just kind of gently bend the number blues, the blue rebar kind of into the same position as where the green was. You could do it like that. Or from a top view, what you could do, if I look at this from the top view, maybe these are my green rebars. And then my blue rebars would do this, and then this, and then this, like that. See? So if you did it like this, your D is not diminished at any point. It's always to the center of the rebar. So the flexural capacity is never diminished with this splice.
Okay, makes sense. And then one more question. Why don't they just weld the end and the starting of the rebar together?
Why don't they?
Yeah. Why don't you just weld them on and call it a day?
No, that's a really good question. I am only laughing because I happen to be on the rebar welding code committee, and nobody ever welds them anymore. It's almost like being on the how to speak Latin code committee when nobody speaks Latin anymore. In the precast world, we weld rebar every single day in and day out. We have to weld rebar. But in the cast in place world, welding rebar, unless this is like some kind of a retrofit or a repair, and that's your only option, welding rebar is pretty much gone the way of the dodo in the cast in place world. Yes, you can. You most definitely could do that. And I'll show you what we're talking about. Instead of doing this, you could bring in a piece of rebar, you can bring in another piece of rebar, and you could full pin weld those two together. Or you could take some lap splicing material, either other little pieces of rebar like this, or steel stock, and you could weld these to the side pieces and make a splice like that. Absolutely, you could do that. Why don't they do it? Because this costs a lot more money than this does, pure and simple. The relative magnitude, this is by far the cheapest. The next cheapest is to use engineered products that are mechanically splicing. So an engineered product would kind of slip over the rebar like a sleeve, and it has bolts that grab it or a grout that goes in there. And you can mechanically splice rebar together that way. That's the next level of cost. And then by far the highest, most expensive way to do it is to weld them together. And the reason why it's the most expensive is just it takes the most skilled labor. It's not easy welding them together. I've had to actually qualify quite a few welders for emergency repairs or something like this, and it's not easy. I'm working with welders who've been in field welding for years and years, and they'll get it, but it takes several tries to pass the qualification test to do that welding. And then you have a guy out there welding and grinding and hammering and welding and grinding and hammering and welding, and that's for one splice, and there may be hundreds of splices. So not feasible. You just don't see it anymore in the cast in place world. You just don't see it anymore unless it's some kind of massive repair and it's your only option.
Makes sense. Thank you.
Sure. Any other questions?
Yeah, Professor. I noticed that we've been working on, beam design, column design. and I've noticed that we haven't focused on connections at all, and I think it might be outside of the scope of this class. But where would we learn, like how to connect like a concrete column to a slab or something like that?
That is a very good question. Unfortunately, it actually is outside of the scope of this class a little bit. Basically, all of us who have ever taught concrete have the same problem. And that is, what do I teach and what don't I teach? Because I could teach this class like 8 semesters in a row and still not run out of material. It's kind of like, I don't know, teaching law. It's like, how much do you learn in law school, and then how much do you learn in the field? And, or I don't know, not to compare concrete design with surgery, but, how much can you actually be taught in one semester? So we tend to leave that out. You're absolutely right. But generally what happens in connections is you either have cast in place connections or you have precast connections. Precast connections, this is one piece of concrete. This is a different piece of concrete, and they come out on trucks, and there has to be some way to support one from the other. So we cast in these corbels, or we'll weld them, or there's all kinds of different ways to connect them. And there's a reference book, if you ever get a chance to look at it, it's really interesting. And it's called the PCI Design Handbook. And it has a zillion billion different ways to connect precast concrete to each other. But that's only for precast. Cast in place concrete is not really connected together as much as it is just cast together. So in cast in place concrete, your rebar would just extend from your beam into your column, and then you would have some hooks on it like so that develops these bars within the column. And likewise, where the column meets the footing, you would have rebar that goes across this interface between the column and the footing. And if you had to have which you will have to have a cold pour, then you have so much rebar that comes up out of the column like this. If you ever go to a job site, you'll see the column partially poured up and there's rebar sticking out. And then what they'll do is they'll come in with the next pour and they'll tie this rebar close to it, and then they'll splice it kind of like this, but the splices will they'll bevel in like this. They'll bend the rebar so that they kind of lap over each other, and then they'll tie it, and then they'll pour up the next floor beyond that. So that was a great question. And the reason why we don't cover it a whole lot is because in cast in place construction, whatever you design the beam to carry, you just carry that into the column. Whatever you design the column to carry, you carry that rebar into the foundation. It's just a continuation of everything. That's why concrete, cast in place concrete, is continuous. Whatever you designed it for, it just continues on because you pour the concrete around it. So it's not like steel, where a steel beam has to actually be welded to a steel column. You can't pour a steel beam into a steel column. You have to connect them. And so in that regard, and hopefully I'm answering the question, but in that regard, precast concrete is a lot like steel construction, but cast in place concrete is really its own animal. Does that help at all?
Yeah, definitely. And would you say that it's pretty, I wouldn't want to say easy, but it's straightforward to pick that up once you actually start working in the firm?
Yes, I would say that, because what's going to happen is each firm has their preferred details. And so as an underling, as a newbie, as the green bean, you're going to go in and you're going to understand the concepts, But you're going to go to your superior and say, all right, what does this firm like to do? Do you guys like the dowel like this, or do you like to project a rebar out of the foundation? Do you carry half of it? Do you carry all of it? And pretty quick, you're going to get a sense of, no. We used to do that until Northridge. After Northridge, we don't do that anymore. We always do this, and this is our preferred detail. I think that's true for really anything you get into. If you go into steel design, you have a gazillion choices in steel. Do I take my steel beam and full pin weld the flanges to the column and bolt the web? Or do I use shear plates and weld the web? Or do I, see what I'm saying? There's all kinds of different ways to skin a cat, so to speak. There's going to be preferred detailing. And so you'll be exposed pretty quickly as to what is the preferred detailing and why. Also, when you have beam to column interfaces like this and column to footing interfaces like this is going to get pretty darn close. Seismic is going to jump in your face. And seismic is just a whole nother ball of wax that is way beyond the scope of this class. So you really can't talk about this stuff too much without really jumping into seismic design.
Got it. All right, thank you.
Anybody else have questions on this material? Okay, well, hopefully I've talked enough that you guys can work through. If you haven't already finished homework 7, that's due tonight, I believe. I posted homework 8, so you can get started on that. Just as an encouragement, homework 8 is going to be the last homework assignment. So the homework assignment that I just posted up today is your last assignment. And we have only got 3 more lectures until the final. So we are getting towards the end here. If anybody has any further questions, of course, you can bring them up in office hour. You can bring them up next lecture at any time. Be honest with you guys, we have 3 more lectures and I have 2 more lectures of material. So now's the time to ask all those pesky questions that I went too fast or whatever happened. We got plenty of time for that.
Professor, are we going to still have a review day?
Sure. Well, maybe not a whole day. But yeah, the last lecture, which is a week from Thursday, I don't have anything planned for that lecture. So if I actually complete the next 2 lectures in 2 days, then we have that whole Thursday as whatever you guys want it to be.
Perfect. Thank you.
Okay. All right. So if we're done for tonight, I give you 2 minutes extra that you can enjoy for tonight. And I will stop the recording and see you all on Thursday.
See you Thursday. Thanks.
Okay.
Thank you.
See you Thursday.